Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, this video is in connection with our previous video where we talked about a series of CFD analysis and optimization of cross-flow heat exchangers, where we talked about different types of heat exchangers with different profiles. In today's video we'll talk about CFD analysis, parametric study and optimization of a cross-flow heat exchangers. In this case the pipe profile will be hexagonal. So without wasting time, let us start our video. The modeling part has already been made. So here in this case we'll go for only analysis, parametric study and optimization. So let us import the model. This is the model. For understanding the dynamics of flow particles, we have made the model transparent. You can see here the profile cross section. It is hexagonal tubes, and in between we have provided 3 numbers of baffles, and this is the exit location and this is the inlet location, and this is the side walls. From the side walls we will be providing hot air 200 degrees centigrade, and from the entry location we will be forcing water at normal 20 degrees centigrade. In this analysis we will try to find out the effectiveness of these cross-flow heat exchangers by finding out LMTD, that means logarithmic mean temperature difference. Initially you have to start with flow simulation, and the flow simulation environment will be initiated with the wizard itself. You can start from wizard. Next to that we have to provide that default name of this project as usual it is coming project 3, so default name of the project will be project 3. Next to that we have to select the unit system. By default we can select SI system, and for temperature as usual we'll take degrees Celsius. Next to that we can see the type of analysis. Here it is internal analysis, and we are excluding cavities without flow conditions. And from the physical features we can select heat conduction in solids, and definitely gravity will be involved because hot fluid will be going off, and the direction of gravity will be Y, which is visible from the direction here itself. So we are providing gravity detection as Y minus 9.81 meter per second square, and along Z it will be 0 meter per second square. Next to that we can see the different fluids. Here in this case we will be considering 2 fluids. One will be air. Let us select air, and the liquid will be water. Next to that we have to define the material. Let us consider the material to be stainless steel 321. Next to that we have to select the wall condition. In this case we consider default outer wall thermal conditions and roughness, and finally we have to select the atmospheric conditions. Pressure will be 101325 Pascal and temperature will be 20 degrees centigrade. Definitely the solid parameters, the temperature will be 20 degrees centigrade as mentioned before. Let us finish this. Now we can see the computational domain. It is being generated. It's preparing the model geometry, and it is recognizing the fluid volume, because for analysis we want to have a closed volume. For that we need to have specific volume inside and closed entity. Anyway, if we want to check that volume whether it is okay or not, we can check it from here itself. Let us check the geometry is okay or not. Let us check the geometry. It is showing status is being checked. Status is successful, so geometry is okay. Next to that we can see the volume generated. Okay, it is showing 100% successful. So you can see the fluid volume is 22.05 meter cube and solid volume is 6.15 meter cube. So status is successful, we can go for a simulation. Right, let us close these things, and we'll see the computational domain. Let us see the domain. This is the domain. Okay, our domain is perfect. Now we can hide this part and go for applying fluid subdomains, because in this case we are having two different fluids. We have to define those fluid subdomains, and for defining these things it is suggested to have a segmented view of this model. So we're planning to cut this one from top plane. Let us cut this model from top plane and provide the fluid subdomains. We've cut that model from top plane. Go and check. Now we have to provide fluid subdomains. As we told in the beginning, that from this entry location we'll be providing cold water at normal 20 degrees centigrade. So that domain should be defined. Insert fluid subdomain. It will be water, and the thermodynamic parameters, it will be 20 degrees centigrade with a pressure of 10135 Pascal. Let us define that location. So this is the fluid subdomain for water at 20 degrees centigrade. Go and check. Next to that, we have to provide domain for the hot air. So we can rotate a little bit to select the specific location. Now insert fluid subdomain again, and in this case it will be heated air at 200 degrees centigrade. So we are planning to conduct a series of cross-flow heat exchangers analysis with same input variables, and later on we can go for a comparative study on performance and analysis of all those cross-flow heat exchangers. So that's why we're keeping the input variables for all those heat exchangers as same. Now the hot inlet location will be the side walls, and from the side walls we'll be providing heated air at 200 degrees centigrade. Right, you can see if you rotate this one, it will be clearly understood regarding two different fluid subdomains. See, this is the volume space for hot air, and from this location we will be providing cold water at 20 degrees centigrade. When you see from this side, the cross-sectional areas of these pipes, it is having hexagonal cross-section, and in our series of analysis we'll change that cross-section areas of different pipes and see the performance of different types of cross-flow heat exchangers, and finally we'll optimize also, right? So this is okay. Green check. Next to that, you have to provide solid materials. Solid materials have already been provided. We don't want to provide any specific material for pipes also. All default material we're considering as stainless steel 321. So materials have already been defined. Next to that, you have to provide boundary conditions. Insert boundary conditions, and as mentioned before, cold water will be provided from these walls, these locations, and let us select the mass flow rate to be 1 kg per second. In all cases we'll be considering the same thing. Mass flow rate will be 1 kg per second, and thermodynamic parameters as mentioned before, it will be 20 degrees centigrade water, right? So first boundary conditions, let us say the thermodynamic parameters is 20 degrees centigrade and it will be water. Green check. Next to that, we have to provide another boundary conditions, that means that hot air. Insert boundary conditions, and in this case we want to provide hot air from the side walls at a temperature of 200 degrees centigrade, and the mass flow rate will be 1 kg per second. In both cases we are considering same mass flow rate. It is done. We have to define two more boundary conditions, that means pressure at the exit locations to be defined again. So boundary conditions, insert boundary condition. it will be atmospheric pressure at the exit locations. Let us select the exit of cold water. It will be environmental pressure. Green check. Another boundary condition is needed at the exit of hot air. So insert boundary condition. It will be atmospheric pressure again. At the exit of hot air, let us select that location. Done. So all the boundary conditions have been applied properly. Next we have to find some goals. Here in this case, our main aim is to find out the effectiveness, and find out LMTD as an equation goal. Before that, you have to find out the temperature at exit location for cold water and hot air also. Let us rotate this model. Now we have to select the goals. Insert surface goals. At this surface, we need to find out temperature of fluid. That means average temperature of fluid at the exit location. By the same time, we want to find out average temperature of hot fluid at this surface also, and we want to create separate goals for each surface. Green check. So two surface goals have been defined. Let us rename these things. First one is cold water exit temperature. So we can rename this one as TCO, cold water outlet temperature. Done. The second one will be hot air outlet. So we can rename this one as THAO. That means temperature at hot air outlet. Green check. Next we have to have that effectiveness, that means LMTD, that will be coming in form of equation goal. Let us select that equation goal, and you have to define that LMTD that will come from the previous determined goals itself. So add the goals. If you know the formula of LMTD, it is equal to del T1 minus del T2 divided by ln of del T1 divided by del T2. So let us define that one. It will be coming from here. It is the temperature at the hot air inlet. That means 200 degrees centigrade minus temperature at the cold water outlet. This is equal to del T1 minus temperature at the hot air outlet minus cold water inlet temperature, that is 20 degrees centigrade. Bracket closed. That should be divided by ln of del T1 minus del T2. So for that you can copy these parameters, copy whole the left hand side parameters, and paste that one here, and instead of minus sign we can replace this one with division. We have defined this one. Green check. So we got the LMTD value as an equation goal. We can rename this as LMTD. Done. We have the goals as temperature at the cold water outlet at this location, and here temperature at hot air outlet. And by using these two different parameters or two different goals, we already defined LMTD, that means logarithmic mean temperature difference, to find out effectiveness of these cross flow heat exchangers. So let us run this one as new calculations. Solve window has already started iterations. Let the iterations move on. Whenever it is finished, you will see the results and go for detailed analysis. The solver is finished and you can see the result is converged. And after 142 numbers of iterations, we got the temperature at the cold air outlet as 156.135 degrees centigrade, and temperature at the water outlet is 20.16 degrees centigrade. That means we found very little increase in temperature of cold water. It has increased by 0.16 degrees centigrade. By the same time, the temperature of air has decreased a huge amount from 200 degrees centigrade to 156 degrees centigrade. It has come down, and by this heat transfer process we got effectiveness of this heat exchanger. We got the LMTD as 156.974. Let us see the other parameters from this analysis. From the results itself, first of all we'll see the cut plots in the form of temperature plots. Insert cut plots, and we want to see these cut plots from front plane. It will be distribution of fluid temperature. Let us see these things. Now we can run this to see the variation of temperature across the plane. Let us play this. You can see that much of change is not there at the extreme opposite side, as we are forcing hot air from this side. At this end we can see huge amount of changes, but other side that much of change is not visible. So throughout these pipes, the temperature of water is that much of change is not visible. It is in the range of 20 degrees centigrade approximately. Again, if we change this pattern from side walls, let us see the variation of temperature of fluid from side walls. Let us close these things. Cut plot 1, clear and hide. Now we want to see all these fluid variations temperatures. We want to see the temperature variation of fluid across the right plane. Right, so again insert cut plot, and in this case we want to view temperature distribution of fluid across right plane. So we can change the plane from here. It will be right plane. Green check. Let us see this temperature distribution of fluid in the form of an animation. Let us play it. And it will be better to see from this side view only. You can see the changes approximately. We can see the changes across the side walls. At here we have huge temperature of fluid indicated by red color, and as it is approaching from the side walls toward the exits location, it is showing that temperature distribution across the side walls, decreasing temperature of hot air, but we don't see that much of changes in temperature of cold water. Right? Fine. Next, we are going to see that dynamics of flow particles. For that, we have to clear and hide these things. Let us clear and hide. Let us see the dynamics of flow particles. Flow trajectories, insert flow trajectories, and in this case, instead of 20 numbers of flow particles, we'll make this one as 100 numbers, and in the form of arrows only we want instead of pipes. It will be temperature of fluid from both the entry and the side walls. So let us select that locations from the side walls. Select other and face at extrude boss base 2, that is the side wall selected. Next we have to select the inlet location of cold water. Let us rotate a little bit and select that specific location. Select other, lid number 1 selected. So from both the locations we are able to see the dynamics of flow particles emerging out from these two surfaces, phase 1 and phase 2. Go and check. So these are the dynamics of flow particles. You can see in a better way. Let us see the asymmetric view. So this is the dynamics of flow particles. You can see in the form of an animation. Let's play the animation. You can see hot air is passing from the side walls, indicated by color, red color, that is temperature 200 degrees centigrade, and as it is approaching at the end of the side walls, its color is green. That means it has lost huge amount of temperature while passing from the side walls. And similarly, when the cold water is passing from entry location to the exit, we cannot see that much of change in temperature. So initially it was having temperature of 20 degrees centigrade, and when it has come at the extreme end position, we can see a little change in temperature from 20 degrees centigrade. It is in the range of 20.2 degrees centigrade approximately. Okay, let us clear and hide these things. And now we have to go for parametric study. For parametric study, we have to start from solve and new parametric study. And we have to start from design for experiments and optimization techniques. The input variables may come from the geometry itself or maybe from the boundary conditions. Let us select those input variables from the boundary conditions, as we are planning to increase in the temperature of cold water outlet. So in that case, we have to select that hot air as the input variable, and that can be selected from boundary conditions. Let us select those boundary conditions. It will be from inlet mass flow rate of hot air. We want to increase both the things, and that means inlet mass flow rate, by the same time temperature of that hot air also to be increased with a specific range. Let us put the range of mass flow rate from 1 kg per second to 5 kg per second. Can check. Next to that temperature range, we should specify a higher range from 200 degrees centigrade to 1000 degrees centigrade. You have defined. Next to that, we have to see the output parameters, and it is dependent on goals. And in this case, we want to see all the goals to be taken care of in this parametric study. That means we want to have LMTD and exit temperature of both the ends. Let us see the scenarios. We have 10 numbers of experiments. To reduce the time, let us decrease the numbers of experiments. Instead of 10 numbers, we want to have 5 numbers of experiments. Let us create those design of experiments. Let us create those temperature ranges at an specific order. Initially, we want to have that temperature to be 200 degrees centigrade. Next one will be 400 degrees centigrade. Third one will be 600 degrees centigrade. fourth one should be 800 degrees centigrade, and the final one will be 1000 degrees centigrade. This will be the temperature, and similarly mass flow rate also have to increase. For the first case, mass flow rate is 1 kg per second. Second one, we'll consider mass flow rate to be 2 kg per second, and third one will be 3 kg per seconds. Fourth one will be 4 kg per seconds, and the last one will be 5 kg per seconds. We have set the design of experimentation, and let us run this one. It has already started iterations. Let the iterations move on. Whenever it is finished, we'll see the results and go for final optimization. Okay, iterations are over, and you can see the design of experiments and optimization is finished. We got 5 set of experimental results, and in all cases we could find that what we expected, that is the temperature increase at the exit of cold water, we didn't get that much of increase in temperature. Initial temperature of cold water was 20 degrees centigrade, and at the highest temperature of hot water, which was 1000 degrees centigrade, at that temperature we found the increase in temperature of cold water is only 0.82 degrees centigrade. That means this data is providing that we're unable to increase the temperature of cold water to a high extent. Even we increase the temperature of hot air from the side walls, that much of increase in temperature in cold water is not achievable, right? Anyway, we can see the LMTD values. In all cases it is increasing as we are increasing the temperature of hot air from the side walls. When the hot air was 200 degrees centigrade, that time we got LMTD value as 156.8, and when the temperature was 400 degrees centigrade, then LMTD is 156.69. At 600 degrees centigrade, we got LMTD 163.54. At 800 degrees centigrade, we got LMTD as 182.50 degrees centigrade. And finally, when the temperature of hot air from the sidewall was 1000 degrees centigrade, then LMTD value is 172.53 degrees centigrade. But in all cases, we could find the temperature of water at the exit location less amount of increase in temperature. So therefore, we don't find any meaning of going optimization of cold water temperature at the exit location. So this is all about our today's CFD analysis and parametric study. Next to that, we'll go for CFD analysis, parametric study, and optimization of another type of cross-flow heat exchanger with a different cross-sectional areas. Okay, thank you so much for watching this video. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.